Other than that chapter 12 treats the three major motions that we have talked about repeatedly: translation, vibration, and rotation. We're gonna solve those systems classically, and then we're gonna solve the systems quantum mechanically, see what the differences are, see where they agree, see where they disagree. Once we do that, I'm jumping to near the end of the book, to chapter 18. It's an extremely important chapter, not enough, of course, to get to it early enough. So what we're going to do is now, if I know all the energies of rotation, all the energies of vibration, blah, 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 what I need to know is what is the statistical distribution of particles among all these energy states. And if I know how many particles there are with what energy, I can come up with a probability, I can come up with an average, and the averages, energies that we will come up with will be the internal energy. And if I subtract PV, they will be the enthalpy, and the entropy, and the Gibbs energy. But this time, not from steam engines, this time it's from fundamental theory. And you will be astounded at how accurate it gets to what has been measured. So that's what we're going. But we have to go through the statistical realm. That means probabilities. Problem number 4 illustrates this. So this is you're going to see again in chapter 18. What it says is that the probability of being in an energy state is proportional to E to the minus EI over RT. The energy is in joules per mole. If the energy were just in joules, this would be KT, because moles is constant, but the problem is given. In this particular quantum system, you have only 4 energy states. You have an energy state equal to 0, that's E0. I'm going to make one mention on this. E1 is equal to 1,000, E2 is 2,000, and E3 is 3,000. Again, all in joules per mole. So what we're going to do is, so now we only have 4, so it's a discrete system. We want to calculate averages and do their things. That's what we're going to do. These are going to be quantum states. And particles in quantum states, and we'll have that probability. So let's go through the problem very quickly. There's one it's fairly straightforward, but the last one to take a little trick, and I want to bring that to you. Also on these is the energy is proportional to E to the minus E over RT, E Joule per mole. We have 4 possible energy states that have states 1, 2, 3, and 4, and the energy of the states are 0, 1,000, 2,000, 3,000. And the degeneracies of these states are 1, 3, 5, and 7. Degeneracy is how many energy states, or excuse me, let me say that more precisely. How many quantum states are there that have this energy? Okay? How many quantum states? And that's usually given the symbol by a G up high, and this has 1, 3, 5, and 7. So I have 1 quantum state that has energy 0. I have 2 quantum states that have energy 1,000, 3 have energy 2,000, and 5 in 2,000, and 7 in 3,000. One point of note that I got an email in, and I have to apologize to you just a little bit. Up in here, someone was trying to redo this, which was perfectly fine. And this was my shot put averages, and I did this with the size of rods and things like that. And when I did this, I carried out my sum from 1 to 8. Well, MathCAD by default starts at 0, okay? But you can change that. I don't recommend that commonly, because you can get yourself into a little bit of difficulties. But to change where MathCAD begins counting at 1, rather than counting at 0, there's 2 ways to do it. You can either just type up here, origin defined as 1. When you say origin equal to 1 or defined as 1, it begins counting at 1 rather than the general default of 0. That's one way to do it. The way I had done it in the sheet, and I'll make a note for future. You can do tools, worksheet options. Then right here it has this array origin. I have it set at 1 just for this particular problem. That's why I started at 1. I didn't have to start at 0. And that confused a couple people, and that's my fault. Okay? All right, now, let's go through the questions on this, because this illustrates all the stuff that we had done here. So I want to evaluate the normalization constant at 298 Kelvin and produce a normalized probability for the system in state 1. Okay? So in other words, I want to know what is the probability of finding a particle having an energy of 0. All right. To do this, we need to add up all the probabilities. The probability is proportional to this, but we can write it in this way. It is equal to some normalization constant times the sum of, this is going to be the G of I, how many there are, multiplied by e to the minus e of I over RT. So I will go from 0 to 3. This, when you add all these up, this is adding up all these probabilities. When you add all these up, when I use the word normalize, you write just like a reflex action equal to 1. All this information you have, it's 1 times e to the 0, 3 times e to the minus 1,000 over RT, you have a temperature, then 5 e to the minus 2,000, and so forth and so on. You'll have 4 terms, you'll add them all up, and you're going to produce a number. That number multiplied by the normalization constant, what we call this now, will be equal to 1. So you'll have n multiplied by a number equal to 1, you'll be able to find what n is. That'll be your normalization constant that we've been doing over and over again. So in other words, in this problem, that is tantamount to this all possible. Okay, so that's the first thing. Once you have done that, then the probability of being in state 0 will be equal to n times G0 e to the minus E0 over RT. And actually, you could do this in general, because you can write it in this way. The probability I will be equal to n times G of I e to the minus E of I over RT. And when you type P of I equals, you'll get 4 values. Okay, so I goes from 0 to 3. And you'll see the one with the largest number is the one that's the most probable, smallest number least probable, so forth and so on. Okay? So that's just doing exactly what we did. The only thing I've added here is this new concept of degeneracy, which we will get to later. Okay? So that gives you the probability. And I say, all right, what's the probability of being in the state 1? Then I ask you to calculate the average energy for this system that a large number of systems would have at 298. So now you're going to be doing this. We get the 2 off here now. So you'll be doing this. Okay, just an average energy as always. Now, you have, now to put this in this context, how this was written, your average energy just follows this scheme. You'll see something like E average, will be equal to, you'll have a summation from 0 to 3. You have to have n, well, actually, no. Do it this way. You'll have E of I times P of I, which the P of I has been calculated here. So you'll have this in place. You've found the N. You now calculate all the probabilities that you need. And you could display them when you do a 4-term array. So now you can just do your E average in this way, just exactly as always. Okay? The normalization constant has been taken into account when we calculated the PI. That's why I didn't it there. So again, it's just straight up what we've been doing. And then you can look at that and say which energy state is the most heavily populated. Well, that goes back to this question. Okay? So this question here gives you the populations of all this essentially. It's the probabilities. So let's say the probability of the first state is 0.4. Well, if I have 10,000 particles, right, then that's 0.4 times 10,000, so you get 4,000 particles that are in that state, you see? So the number of particles will come into play, but the probability is what you're after. So you look at this number, the largest, the state with the largest probability is going to have the state with the most population. That's it. So what is the probability then? Now we're going to do another state, and we're going to use the AND. You know, I remember we had an OR and an AND we multiply probabilities together. But in problem D, or part D, it says the probability that a combined energy of two of these separate systems, described by the probability distribution, will add to 3,000 joules per mole. Well, now you're going to have a P1 of I and a P2 of I. And there's actually a better way to do this. I'll show you, I'll tell you, explain why in a moment. Let's do an I and a J. So you'll have I defined as 0 to 3, and then you'll have a J defined as 0 to 3. All right. Now we have to be very careful. We have a total sum that adds to 3,000 joules per mole. Okay? Well, that means I can't have the state 0 or state 1, I can't have it in 0 and state 2, 0. That would be an energy of 0. So we need to find all of the combinations of states that will add up to 3,000. So I could have it in state 1, I could have something like this. I could have it 0 and 3,000 in that state. I could have 1,000 and 2,000, right? I could have 2,000 and 1,000. And I'm going to have 3,000 and 0. All right, so for each of these states, you have a probability. So the combined, so this is going to be an AND. The total probability will be this probability multiplied by this probability, or the probability that you get. Okay? So the probabilities, your total, this will be P0 times P3. This will be P1 times P2, P2 times P1, and P3 times P0. So those are all your probabilities now combined, because we're using the word AND. You multiply probabilities when you add. Well, you're going to get a number for all of these. You're going to have to now renormalize. Okay, all these numbers have to add up to 1, because those are the only possibilities. Once you do that, let me think about that. Read the question, maybe cast it a little bit differently. With the probability that combined two separate systems described that a given probability will add to 3,000 joules per mole. Okay. Well, you'll just simply have these probabilities. You'll simply add all these probabilities. I can take that back. We're not renormalizing. We're not changing the system. All right. So I just want to know just the probability of adding 3,000 joules per mole. So combine those, add those, or multiply those out to get your probabilities, add the total, and that'll be all the combinations. Okay?
Doesn't it change the probability if, like, say we know that P0 is 0, does that not eliminate one possibility?
The energy is 0, the probability is not.
Okay.
Okay? So when you do this right here, you're going to get an array. These are all going to be non-zero values. So having an energy of 0 still has a certain probability. It doesn't contribute to the energy, you're correct, but there's still the probability that it will be there. Let me take you back to, we were doing heat capacity for vibrational systems. We found out last year that in vibrations, molecules are usually at in just a fundamental ground state. Well, that is usually set at a value of 0, okay? We'll get to that. So even though it has virtually no energy, actually this works better for an electron in an atom. An electron in a ground state has an energy assigned usually as 0. Except for other circuits, we'll get to that. So the energy is 0, but the probability of being down there is almost a certainty. The probabilities and energy values are different. So that's why these will be probabilities, add them together, that number, since it's all normalized, that number will be a probability of having that 3,000. Okay? Now, this is the trickier one. In the last one, I want to compute the average total energy for the two systems at 298. Okay? And then I ask what is the relationship does that result have? This is a mathematical argument of what is a fundamental theorem of statistical mechanics. We will get to this, but here's the deal. In order to calculate the average energy, your average energy for two systems will be this. So now the average energy for two systems will be, we're going to have another summation. You're going to have energy of system 1 plus energy for system 2. That's the total energy. Again, multiplied by the probability of being in that energy state. So you'll have P1 times P2. That's the probability of being in an energy state of E1 plus E2. Now here's how I suggest you do this, just to make life easier. If you set this thing up in, as I suggest within here, you can combine it. What you really have to do, I'm just showing you a shortcut. What you have to do is essentially this for all possible combinations. You're going to have P0, 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 P1, P0, P2, P0, P3, and then a P1, P0, P1, P2. You see, you have to do all the possible combinations. Well, you can do them out and write them all out individually, or you can take advantage of a double sum. The way I did it, just to show you an easier way to go about that, is to do this. Make this a summation and a summation of I and J of EI plus EJ times PI times PJ. Okay? So here's what MathCAD will do. It will start I at 0 and have J at 0. It'll go E0 plus E0 times P0 times P0, and it'll give you a value. Then you'll say that's 0 and J1. And it'll do 0, 1, 0, 1, and then 0, 2, so 0, 2, 0, 2, so forth and so on. Once it's gone through all the J's, it'll now set this at 1, and we begin your J's at 0, 1, 2, 3. You see, so it will automatically do all the combinations if you do this. But the total average energy is this average here multiplied by probabilities of two states having a simultaneous value. Okay? What you should see is when you do your average with a single system in part B, you're going to come up with a number. It's something like, I don't remember exactly the number, like 1,020 or 1,070, something along that line. It's 1,000 something. What you should see is that two systems combined, the average energy is simply doubled. Really, just you add the two systems together. What that tells us fundamentally, we will return to this in chapter 18. It's a fundamental theorem of statistics, statistical mechanics. It says if all the systems are identical, think Avogadro's numbers of identical molecules. All of Avogadro's numbers are identical molecules. If we know the probabilities and averages of one molecule, all we need to do is to multiply that value times the number of molecules that we have. That is very, very, very convenient. I mean, you don't have to worry about all individuals. So that's gonna be something we will make use of. So it's a good problem to kind of illustrate this. But this is your fast way of doing that last part. So I thought I'd kind of throw that out there for you. Okay. All right. To finish off this, then we'll just introduce a little classical mechanics. We're going to take a short ride through classical mechanics, so we see how that develops. And before we then turn ourselves, what we'll do with the classical mechanics is we'll first kind of develop a couple of relationships that you probably saw in physics, hopefully. Although I understand they don't cover this completely. But then we're going to take that classical system and we're going to use it to solve for the hydrogen atom like Bohr did. Bohr only had classical mechanics. That's all he had. So we're going to solve the Bohr model to see how he came up with his results and why he didn't know why. And then once we do that, we introduce quantum physics, then we'll rebuild the universe from there. Okay, but the last part of this, we have discrete values such as this. We have functions that sometimes reproduce those discrete values, like we had done down here, where I just kind of invented representation of discrete data by equations. But again, if we can treat things as continuous, then an integral turns into a sum. So what I've done now, that little formula that I had for doing our shot putters, I had 100i, where I was an integer, 1, 2, 3, 4, 5, 6, 7, 8, and I plus 1. I said, well, now let's make x continuous. It could have any value from 1 to 8, okay? So now, when I do my normalization, because all the probabilities still have to add up to 1, so the first thing we do is when we have a probability is we have to normalize it. So I say the integral of n, whatever that constant is, we have to find it. N times this integral, this is adding up all the probabilities over all possible states, must be equal to 1. So now this just becomes a mechanic exercise of doing the algebra in it, where I have now 1 is n times the integral from 1 to 8. I have 100x over x plus 1 cubed dx. Well, to do this integral, the easiest way to do it is, say, to let y equal to x plus 1, then dy is equal to dx. And x then becomes y minus 1.
How did you get the integral? Like the integral itself? How did you get 100x over x plus 1?
That was, I built that, from the data that I gave you from the shot puts, I built it essentially empirically. I just came up with an equation that fit the data. And so I made it up out of my own pea brain, is what I came up with. So there's nothing magical about it. I said, well, this fits the data pretty closely. Okay? So in here then, just to do this fairly quickly, this becomes then n integral. Now this is x equal 1 to x equal 8. So y is x plus 1, so this now integral becomes 2 to 9. So I'm transforming the x from x space into y space. Then I have, I'll take out the 100 here. We don't need that in there. X becomes y minus 1, and the y x plus 1 cubed just becomes y cubed. Now this becomes dy. So just doing a simple substitution, I can break this up. I have 100 times n. Now this will be multiplied. I have an integral from 2 to 9 of 1 over y squared. So y divided by y cubed, 1 over y squared dy. Then minus integral from 2 to 9 of 1 over y cubed dy. So now they're straightforward integrals too. You guys see it? Francis, see it?
Yeah.
You had that kind of Greek brown look that said, where did that go? See what I did? This is the common denominator now. So it's y over y cubed minus 1 over y cubed. Okay? Well, now it's straightforward to solve. It's 100 times n. This becomes now minus 1 over 9 minus 1 over 2. If I do the integral and then evaluate it, this negative becomes positive. I have a 1/2. Then 1 over 9 squared minus 1 over 2 squared. Okay. So I'm just doing the integrals and evaluating. And again, this is equal to 1. So I just plug it in and let the calculator or computer produce an answer. And when you do that, here's the results in here. I went ahead and transformed back, it doesn't matter. But you can do it either way. But it gives about a 27.006. That has to equal 1, so n times that number is 1. So n is 1 over 27.006. And so the probabilities are n times f of x.
And so n will be different for each and every probability. Like for question 4 for the homework, will each and every n be different?
Unless I artificially limit it. I say, okay, we have our 0, 1,000, 2,000, 3,000. Is now, I have a new system where it is impossible to be in 2,000. Now I've altered the availabilities. Now I will renormalize. But since I have not eliminated any possibilities in that problem, the n will remain the same. All right? So as it will be in this case. Okay? But if you limit it, it's a boy-girl problem again. If you eliminate the possibility that there's a girl, then you renormalize. Okay? So anyway, this is the probability again. This is from above, and here's the P of I that I just calculated from here. So we have about, they're fairly close, so not quite as good. You notice that when we did the discrete one, we got better values than these. Well, the reason was that I pointed out last time. The spacing between the probabilities is too large. Or whatever it is, we got something like this. So when we try and do an integral over this, you know, we have these spaces here that are causing an error. That's going to, again, when we do a quantum system, we're going to make this evaluation of how tight these things are, how close they are together. That'll give us an idea of how much error we will incur. So we get something in the general flow, but the numbers are not nearly as good. Well, now we can play the same games we had done before. If I want to know what is the fraction of individuals that are greater than 5 yards, well, I do an integral from 5 to 8. And since it's all normalized to 1, if I go from 1 to 8, it gives me 1. 5 to 8 will give me a fraction, or say about 17.7%. And then once again, the average distances, we do averages just as before. We have a normalization constant, value, times the probability, carry that out. And again, using the same substitution that I did before, we just do a little bit more work on it. We get an average distance of 3.129. When we did the discrete summation, we got 2.756. So again, that error is kind of biting us a little bit. It's an important thing to understand. Average square distance, 13.02 compared to 11.467 above. And so the root mean square is now 1.816. So everything's done exactly the same way, except instead of carrying out some, they're just doing an integral.
And the integral, will we have to figure out what the integral is?
When we solve quantum systems, then we will be doing the integrals over known functions. We will know those functions. So what I'm going to do is I'm going to come up with, for example, a wave function for a vibrating particle. All right, well, there's the wave function. And we're going to learn how to get probabilities from wave functions. We got a wave, we got a probability. Once we do, you'll have that function in hand. So we'll normalize it immediately. And then from there, say, all right, what is the average? So if a particle is vibrating, what is its average amplitude? Or an average position or something like that. But it'll all be done in this way.
And this one is for continuous systems.
Continuous. If I can treat it continuously, it is an integral. If I can't, then we'll have to do a sum. Okay? All right. What we will find is that translation will be able to treat continuously. We'll see why. That's why the Boltzmann distribution, which is classical mechanical, that's why the heat capacity for those things was so good. Because the states are so teeny, so close together, that an integral works perfectly. When we get to vibrations, no way, Jose, not a chance. That's why the heat capacities and energies for vibration were so far off. It's because we ran into this problem. Okay? So we will see that going forward. The concepts are built here. All right. In going forward, in some of the classical mechanics and also then in quantum mechanics, again, this is not a course in differential equations, but I want to introduce you to 3 that you can write the answers down for immediately. All right, so these are straightforward. So I just want to give you these. The 3, one looks like this. We're going to see a lot of double derivatives, as you will see. Okay? So here is a differential equation. In this, k is a constant. Okay, this is very important. It's just a constant by itself. Very important. In this type, we can do what we've done many, many times in the past and do a separation of variables. So in solving a system of this for mechanics, whether quantum or classical, I will begin by doing this. Equals minus k, to bring it over to the other side. Then I will bring a dx over to here. So what I will have is a dx of, let's see what sorry, I put it that way. There we go. dy dx is equal to minus k dx. Remember, this is actually a dx of dy dx. Just remembering what a double a second derivative is. So I just took one of the dx's across. We have that. Now, when we integrate indefinitely. Okay. When we do that, this becomes minus kx plus a constant I would just call C1. It is an undetermined constant. We'll see how to get those. So now, and of course, this is now equal to dy dx. Now I've done that. I will now do that because I'm going to rewrite this. Now I have a dy dx as minus kx plus C1. Now I want to do it again. So I have a dy integral, which will be equal to y, is going to be the integral of minus kx plus C1 dx. Equal sign between there, sorry. Okay. When I do that, this y now becomes minus kx squared over 2 plus C1x. We have a second constant integration. So if we have two derivatives, which was most of the case, you'll see why later, then what we're going to end up with two undetermined constants. This is called the general solution. Okay? This is the general solution. Now what we have to do is we have to apply two different terms. If it is in classical mechanics, I have to apply what are called initial conditions. What this is tantamount to, so this is now a distance. Let's say this is a distance, or a distance, whatever this may be. I have to evaluate by the C1 and C2 by saying, well, when x is 0, what is y? I have to say that. So if x were, say, time, for example. So if this were an equation that gives the distance y as a function of time. So, all right, well, what is the height, if we say y, what is the height y when time is 0? We say, well, it could be at the ground, or it could be 50 feet up, or whatever. So that would determine what this is. And then the second initial condition that I will need is to say, well, how fast is it going when time is 0? Or that takes us back to this. What is the rate of change when x is 0? If I put a 0 in for this and I define what the rate of change is, 50 meters per second or whatever it may be, it'll tell me C1. So in order to determine those constants, they're easy to do. We just need to know what the system is and what the initial conditions are. So we have to define two initial conditions to begin things. You're going to be doing one, we'll talk about it next time. You're going to have a particle that's attached to a spring against the wall. Well, I need to know when we solve the equations of motion, but I need to know, well, what's happening. What we will end up doing is I say, okay, I'm going to take that particle, I'm going to stretch it out to some distance. And I'm going to say initially, it's okay, well, its initial position is here, its initial velocity is 0. That'll give me my constants that I need, and then I let it go, and then it does its thing. Or I can say, well, its position 0, but it's moving with this velocity. You see, once I've defined that, then we'll move on down the road to solve that problem, okay? Now, in quantum mechanics, we're going to be dealing with waves, so the term will change. process is identical. It's just a semantics difference. In waves, we're going to be looking at what we call boundary conditions. What is the value of the wave here? What is the value of the wave there? Once we do that, then we'll be able to do, we will get to that. But just let you know, when I use initial conditions or boundary conditions, they mean exactly the same thing. We're always going to produce a general solution, then establish what the system looks like. Then we'll be on down the road fairly easier to do than it is actually to explain. All right, so that is for this form where I have a K all by itself. There are two others, and these we don't do any integration, we simply write down the answers. So, and here's my discussion about initial or boundary conditions. So differential equation number 2 looks like this. We have d2y dx squared. I have the first one as a minus ky is equal to 0. Okay? Now, I cannot do a separation of variables on this and integrate because we don't know what y is. I need to know what that looks like before I can do the integration, but I need to do the integration to find out what that looks like, and then we're making it. So what we do is we write down a general solution that is known to be the solution to this. When you see a second derivative, a k times a y, not a y squared or anything else, just a y, and a negative sign. That's important. When you see that, you simply write down the answer as follows. You say y as a function of x then is equal to, I have an a e to the square root of k times x plus b e to the minus square root of k times x. Okay, so they are real exponents. They're not complex. We'll see a complex in a moment. Secondly, whatever this constant is here, it must be positive. Must be positive for this to be correct. If this is a positive constant, the solution is this, where the constant ends up into a square root. So we have a positive square root of k times x and a negative square root of k times x. This a and b are the equivalent of the constants of integration. Those are the undetermined coefficients. And again, once we establish initial conditions or boundary conditions, we will be able to determine what those are. To prove that this fits this form, I should do a derivative and a second derivative. If I take dy dx, this becomes a times the square root of k times e to the square root of k times x for the first derivative on that. This becomes minus b root k e to the minus square root of k times x. So that's the first derivative of that term. So I just simply, the a, square root of k comes down, I repeat the e. Let's do it again. A second derivative, dy dx squared becomes, now I do it again, so it becomes a, I get another square root of k, so it's a times k e to the root k x. And this, I got another negative root k, so that comes down here, makes that positive, b k e to the minus root k times x. This, if you look closely, is k times y. Because if I pull a k out from this, I get a e to the positive root kx, b e to the minus root k, that's that. So it repeats that. So ky, well over here, that's this. So ky minus ky, of course, is 0. So it's, okay? So that's just going to do, why should do that once. That's one that we will see. They're exponentials, they're real, you must have a negative sign. If this becomes now a positive sign, there are two different answers. The answers here are either y of x is A e to the I root k times x plus b e to the minus I root k times x. So it looks almost identical to the one with the negative sign, except it has a complex number in it. It has a square root of -1 in the solutions. And once again, if you take two derivatives of that, it'll come out to minus ky equals ky will give you 0. That's one solution. The other solution that is essentially equivalent looks like this. I'll use, instead of A, B, I'll use C, D. It's becomes C times the cosine square root of k times x plus D times the sine square root of k times x. Okay? Both are equivalent because if you recall, e to the ix is cosine x plus I sine x, or actually I'll say plus or minus, and I'll have plus or minus. That Euler's relationship that ties together the trigonometric functions sine and cosine to a complex exponent. So you can show fairly easily that these are equivalent, even though the coefficients A and C, B and D are not. These are not the same value. These are not the same value, but the equations themselves are equivalent. That can be easily shown where I do it in the last page of this. I have a sine and cosine, so I put them all together. And here's my complex exponent, there's my sine and cosine, and there's a relationship. So the C is A plus B, and the D is the I times A minus B. Yes?
So if we're going to do a problem that involves this bit, how do we know which one we should go?
You swung right into my next comment. Thanks for letting me right into that door. The answer we will find will be dependent on whether the system is bounded or not. Quantum mechanically, here's what we will find out. Quantum mechanically, this will represent a quantum particle having a positive momentum. You'll see why later. And this will be a particle having a negative momentum. So the first thing we will do, or first quantum system we will solve, is a particle in free space. There's nothing else in the universe except that particle. And so what we'll do is we'll come up with a solution very much like this. One's going to represent the probability of the particle moving forward. One's going to be representing the probability of the particle moving in reverse. So that turned out this would be the easy one. Once we do that, after this exam, the first thing we'll do in the next exam is I will take that particle and say, I want to know more about where it is. I'm going to put it in this room. When I put it in a room, that now limits the bounds, binds the particle to being limited. It can't go past that wall, can't go past that wall. When we do that, we will find these will be the easier solutions. Both will work. One is easier than the other, and I will guide you on that.
And I here is, what is I here?
I is a square root of -1. It is complex, which causes somewhat of a difficulty. So if this is, let's say this represents a particle in space, and that's the wave of that particle. Well, how do you describe a particle in space being a real thing when it is involving an imaginary number? One of the conundrums that we'll have to work our way around, and we will. Okay? All right, so those three differential equations, you should be able to kind of see the answer and write it down. And that'll be just kind of, we don't have to do. When they get more complicated than this, we will not go through that. I'll just simply provide a few solutions. Okay? But these we'll see many, many times, so it's worth discussing. All right, with that, we do just a brief introduction, and then we'll pursue this next time. Again, before the path through quantum mechanics begins with classical mechanics. So this is done, thousands of years ago. Galileo developing doing the laws of mechanics, and of course these then become what we call the postulates of classical mechanics, the first laws of classical mechanics. The laws, as you know them, is that the momentum is the mass times the velocity. And so the momentum is the dr mass times dr dt, which that's the velocity. The derivative of the distance with time is, of course, the velocity. The other thing is the force is what you're typically given is force is mass times acceleration, but in reality it's better described as force is the derivative of the momentum with respect to time, or mass times dv dt. And of course, dV dt is the mass times acceleration. Postulate number 3 is the one that is most misstated. It says, that is one commonly referred to is that if there is an action, there's an equal and opposite reaction, right? Well, there's a condition on that. And the condition on that is that the two objects do not have an external force acting on them. So if the objects are in space, like you're standing in space, and you want to spin around, you can't do it. You turn your upper body will turn the other way. You can't do it. But if you're falling in a free fall on Earth, you've got air rushing around you, you can. You can twist yourself all any way you want to. So that is an external force acting on the internal forces. So the force total on any type of system is, these are the internal forces. We have particle I, particles J, and these are the forces between the particles, and I call those internal forces. And then we have the external forces, that would be gravity or whatever, magnetic field or whatever it may be. And that's the total force. And so that, of course, is by the second law is derivative momentum with time. The sum of the forces, if this is the total sum of the internal forces is 0. That's the third law, is that term is 0, not necessarily that term. So it has to be just particles within itself with no external forces. So here is found the acceleration on a system depends only on the external forces applied. If I have a molecule, it's vibrating, this is where it is. A vibrating, rotating molecule, the forces that are acting to hold it together, to spin it around or whatever, doesn't matter. All that matters is where its center of mass is going. So that kind of separates that. So Newton's third law effect. You'll see that. And then a couple of minor energy considerations that we will come across. It turns out that the work is force times dx, or the potential energy now. So the force on an object turns out to be negative, the derivative of the potential energy with x. Think about it this way. Remember drawing curves that look like this for a molecule? We had them empirically before, but that's what they look like. This was the potential energy here, and that was the distance between two particles, the radial distance. So that said that when the particles come closer together, the energy goes down. It reaches a minimum here. If you get them too close to each other, the energy begins to skyrocket. Well, if the particle is over here, then there is a negative, force acting on it to try to bring the particle down here. Let's think about this: a ball in a well on Earth. So there's gravity, force of gravity is going to try to pull that down. Well, that is minus dv dx, or the slope at that point. So those are the forces. We're needing that's a very important one. And then finally, I use an example of the gravitational potential. Well, the potential energy of gravity is mgy. It's the scheme. So what is the force of gravity? Well, it's derivative of minus dv dy, which is minus mass times the acceleration of gravity, which is known as mass times acceleration of the force of gravity. Okay. And then just a couple of quick examples. If I had a potential energy on a particle, and the potential energy had a potential that looked like minus x minus y squared times x, what are the forces on the particle? Well, the force in the x direction is minus dv dx, so I get 1 plus y squared if I take that derivative. And the force in the y direction is minus dv dy, and so it becomes 2yx. I can evaluate that at a position 2 and 6, so I know at position x2, y6, I know what the force is going to push that particle. And then we use the equations of motion, which we'll get to next time, to find out, okay, well, at 10 o'clock, where will they be? So we're going to all these forces. And when we were talking about that, you and Jennifer were talking about the molecular mechanics, that's what it does. It does exactly that. So the molecular mechanics, which all of you will see soon, molecular mechanics defines all of these. So this is, if there are modeling software that gives you structures, proper structures for molecules, what should they look like? Well, it uses exactly this. It says I have a force acting on these particles between each other, and it just does mechanics of motion and finds out what the forces are until it comes down and finds what equilibrium position. We will get to all that. All right, so we'll do a quick classical mechanical solution next time, go into a spherical frame, and we'll do more on. So we'll be getting on to that. Oh, by the way, problem number 5 is just an integral, and I'm just giving you a different function. So what we had done in the previous, where that last bit doing the integrals of the probabilities here. So we're doing, the only difference is I gave you a different probability function, and now we have ages of the population rather than chocolate going. Okay, so it follows this exactly.
4 and 5. 4 and 5.
Yeah, 4 and 5.